How about now? Test? Great. Okay. Had some horrible feedback. How's the feedback now? Okay. I think we're set to go. I'm going to share screen and then pull up the presentation. Everybody should be able to hear me and see this now. So, any questions from last time? Online in the class, everybody's happy. Expect to see another homework posted. Exam 1 week from today. You should have notified me if you need to do something other than the room that we're scheduled in. So we're scheduled to have the exams in the room. We've got a few rooms. I'll have to post those again. Usually we had 2 rooms last time. It'll probably be the same 2 rooms. And then if you did not think it could get any better, it is getting better. Next week, we're going to meet 5 times. Tuesday is a Wednesday schedule. And Thursday night is the only time I can do a review session. And if you want to count the exam, that makes 6 times. So next week is your week of fluids. Dress appropriately. Write in questions if you have questions about that. And again, the review session, unfortunately, I've got all my afternoons scheduled next week. So plus I've got classes almost every day. So Thursday afternoon, which is the night before your exam, that's probably when you're going to be studying anyway. It's the last minute. So the review session, I'll probably start around, I don't know, 3:30, maybe earlier. I don't know. I have to look at my schedule. And again, it's all online. We address homework problems. If you can't make the review session, it's not the end of the world. Contact me electronically, set up a Zoom meeting, come by my office, shoot me an email. I'm sure we can answer any questions you may have.
You have class Wednesday though, right?
We don't have class Wednesday?
Yeah, it's Veterans Day.
It's what day?
Veterans Day.
Veterans Day, is that a holiday?
Yeah.
You just made my day.
Oh, okay, cool.
Anybody who saves me time is a hero in my eyes. All right, so evidently I was just told Wednesday is Veterans Day, and what's your name again?
Travis.
Travis is giving everybody in the class the whole day off. All right, so this is the momentum equation that we've been dealing with. And for this momentum equation, we can apply that to any control volume, particularly when we see that the geometry of the flow field is changing and there are significant velocities involved, and the velocity vector has a significant change in that short distance. And then we started off last class talking about fixed vanes. And the nice thing about the fixed vanes is that you have all free jets in these systems, and it makes the analysis really simple. Really, the resultant force is the force on the vane, and there's no other forces. Now, you could have some very specialized problems, for example, submerged systems, and you could have submerged jets on submerged vanes. Okay, I'll leave that to when you graduate and you're actually working in real applications, but you should be able to do this. In that case, you don't have free jets, you have submerged jets, but the analysis would be the same. And again, I've given you this rubric on how to do these problems, and this is the last time you'll see it today, but we always use that rubric when we're doing a momentum problem, and you should be able to get through it nice and easy. And again, what you're ultimately after to perform the momentum analysis is at the bottom of this slide. You know, we need to have the pressures, the flows, and the velocities to perform the momentum analysis, and ultimately we will compute a resultant force. Again, fixed vanes. And then last time we talked about a vane example, and this is the example we went through. Did we do this last time? I think we did. Yeah, we did. Yeah, and so in this example last time, again, what you have is a single vein. And that means it's not only one vein all by itself compared to a series of veins like you might see on a turbine or a pump. This is just one vein, like a snowplow or the scoop under the old steam engines. They would have a trough of water between the rails. They'd drop the scoop and the water would scoop up and fill the hopper again with water so the steam engines could keep going. So there are many instances of single veins. And what we did was, in this example, we came up with a control volume. And for that control volume, we analyzed the system for these resultant forces. When you have one entrance or one inlet and one exit, these are the equations you get. If you have more than one entrance or more than one exit, you will not get these equations. They'll look like these equations, but you just have more terms. So these two terms, the rho QV and the rho QV cosine theta, represent the momentum fluxes entering and leaving. If you had more locations where the fluid was leaving, there would be other terms on this equation. And same thing for the other equation. Okay, so just be aware of that. You're going to see these two equations again because the examples I'm doing today are going to be just a simple vein with one location of fluid entering and one location where fluid's leaving. I don't need to recreate these equations unless you really want me to. I certainly will. So where we ended last class was we can have a vein now. And for example, go back to our original little vein that looks like this. And we have a jet coming at it at V0. But now the vein can be moving either towards or away from the jet. So now the vein is moving. And this is an unsteady problem, which means we can't apply energy and we can't apply the momentum equation because both of those equations were developed for steady state systems. So how we convert this unsteady problem to a steady problem is to become an observer moving with the vein. And so in that case, the vein is sitting still. It's a fixed vein problem. And now what you have is some relative velocity approaching the vein. By becoming an observer moving with the vein appears to be fixed, which makes this a fixed vein problem. And the last equations with modifications are appropriate. So for the moving vein analysis, the first thing we need to do is convert the problem to a fixed vein problem. So again, this is the system as you see it as an observer just sitting in your sofa or sitting in your chair. The vein's moving, fluid's coming on at V0 and it's leaving at V2. And sometimes V2 can be almost 0. If you think about a moving vein you have seen dozens of times, if you live in New England, snowplow. Is the snow on the road moving? No, it's got a 0 velocity. But when the plow comes by, it shoots off the plow. So V0 and V2, when this is an unsteady problem, are two different velocities. However, if you become an observer moving with the snowplow, it appears that the snow is coming onto the plow and leaving the plow almost at the same velocity. Okay? So that's the difference between unsteady and steady. And so we need to convert this to a fixed vein problem. If V0 is the approach velocity, U is the vein velocity. And again, you can be towards or away from the vein. And that's what distinguishes a pump from a turbine. And there are a lot of instances when V0 is 0. I just gave you the snow. How about a ship and a propeller? The ocean is just sitting there and the propeller is actually moving through the fluid. The fan you put on in your room, the air in the room is more or less just sitting there and the fan all of a sudden is generating flow. So these are vector equations and I should have put the little arrow above them. And as vector equations, what we need to do is in a vector manipulation, subtract u from v0. Again, that's a vector manipulation. So when we do that, that gives us the relative velocity. The relative velocity vector is VR, and it's equal to the approach velocity vector minus the vane velocity vector. And this creates a fixed vane problem. So the fixed vane problem now is the vane is fixed. It's not moving at all because you're an observer moving at you, moving at the vane velocity. And now what you have is the relative velocity going on and off. This is true in a horizontal plane. If you have a vertical plane, that's not true. VR reduces in the vertical. Again, the example I gave you last time was shooting your garden hose into the air. And since this is a moving vane, now what we can do is start to look at power. And the power either put into the vane or the power the vane takes out of the problem, takes out of the fluid, whether you're looking at a pump or a turbine, is the horizontal component of the velocity times the vane velocity u. Because again, the vane is sitting some distance away from the center of rotation, and this force is being applied at a certain rotational speed. So force times velocity gives you the dimensions of power: force, length per time, Newton meter per second, or foot-pounds per second. Foot-pound per second can be converted to horsepower, as you saw when we were talking about energy. Newton meter per second is a watt, and we typically just convert that to kilowatts. So let's do an example now that we've kind of walked through the principles of the moving vane. I'm going to show you a single vane. And again, after we finish single vanes, we'll talk about series of vanes. And there's just a minor manipulation. That's all you have to worry about. So for the single moving vane, what you're trying to do is calculate the force components parallel and normal to the approach jet due to the water jet. What is the rate of work being done by the vane? So this is what the problem looks like. It's in a horizontal plane. And these are just construction lines, parallel construction lines. And what you have is a vane whose final angle is 10 degrees off of the horizontal. So if this went fully and turned the fluid all the way around, that would be a 180-degree angle, right? However, it's not going through a full 180, it's actually turning the fluid through 170 degrees, okay? And again, what the problem we did last class, we had a simple 30-degree angle. But again, this angle is what will be used in the equations we developed. Last time I explained that no matter what the angle is, you get the same equations for Rx and Ry. So we're going to have an approach jet coming at this vane at 120 meters per second. It's always good now and then to use SI so you remember how to use it. I have yet to do a design project in the United States that uses SI. Some federal agencies want to see it in reports and scientific reports, but in this country, we're still using BGS. The cross-sectional area of the approach jet is 0.001 square meters. And obviously, if I multiplied those two together, I would get the approach discharge, 0.12 cubic meters per second. The vane, however, is running away from this approach jet at 40 meters per second. That's obviously slower than the 120 meters per second. So this jet is going to hit this vane right along the surface and come off of it. And it will come off of it at some velocity. And that velocity is not 120 meters per second, as you'll see. So the question asks for, this is Rx, the force components parallel and normal to the approach jets. So as before, Rx and Ry. And we can certainly add those together to get the total vector capital R. Okay, so this is basically the problem. And after you get Rx and Ry, the next problem is what's the rate of work being done, meaning what's the power? Vane power, PV, okay? So these are the steps. You first need to create this unsteady problem to a steady problem by removing the vane velocity from the approach velocity. So in this case, so these are the steps that were on the previous slide. I'm going to zip back really quickly. So these were all the steps on the previous slide. So the relative fluid velocity is 120 meters per second. That's V0. U and V0, we call to the right the positive x direction. So V0 is a positive 120, U is a positive 40, V0 minus U is 120 minus 40, or 80 meters per second. Okay, so now that it's a fixed vane problem, you have VR as 80 meters per second coming on and 80 meters per second going off. Remember, this is in a horizontal plane. And what we do to demonstrate that you have that velocity is just write a Bernoulli equation from the inlet before the vane to the exit after the vane. P over gamma 0, it's in a horizontal plane. Both of the Z values are the same. V entering has to be equal to V leaving because it's in a horizontal plane. So then we want to calculate these force components. And again, we have already derived that we can get the force components from a momentum analysis of the vane on the control volume of the fluid just entering and just leaving the vane surface. Would you like to see these developed again? Yes? Yeah. You know, it's Friday. Even I deserve a break on Friday. I'm just adding a slide or two. Okay. So here is our vane, and we have 80 meters per second coming on and 80 meters per second coming off at a vane angle equal to 170 degrees. And the next thing we do is draw the control volume. So the control volume is going to start just before and go to just after the vane. That's my control volume. And then as we have done before, again, I'm just going through all those steps I said I wasn't going to put on the board again. Here is our coordinate axis system. And Z is equal to 0 in the plane of the vane. Okay, so again, I'm just going down the steps in that rubric. So for this, we've got a rho QV term entering here. And let's call this and this is rho QVR. And this is entering, and we've got rho QVR leaving. And that rho QVR has a component in the horizontal direction, and it has a component in the vertical direction. And then again, we assume that we have this resultant force vector. We're just assuming the direction, and it has components in X and Y. And so then what we would do is say in the horizontal direction, sum of the forces in the X is equal to the sum of the momentum flexes in the X. The only force component we have in the X is Rx, and it's directed in the negative X direction. So minus Rx is equal to the rho QV term entering, the velocity vector is in the positive x direction, and the rho QV term is entering, which is a negative. Negative times a positive is a negative minus rho QVR. And then at the second location, we've got a rho QVR cosine theta term. The VR cosine theta is in the negative x direction. And the term is leaving, so that's a negative. But as before, what we're going to do is, if this thing had only gone through 30 degrees up to 90 degrees, the cosine of theta would be a positive number. Once theta gets to be greater than 90 degrees and up to 180 degrees, cosine of theta is a negative number. So I'm just going to leave that as a positive rho Q VR cosine theta, because I know the cosine of theta is going to give us that sign on the velocity vector. So therefore, Rx is equal to rho Q VR 1 minus, sorry, yeah, 1 minus cosine theta. Again, because theta is 170 degrees now, that minus cosine theta is like cosine of 170 degrees is like 0.98 minus 0.98. So it'll be 1 plus 0.98. So if you look in the y direction, the only force we have is Ry, and that's in the positive y direction, and that's equal to the sum of the rho QV, and there's only one term in the y direction. It's again equal to rho Q R. And so if you go back, to the where this all started, yep, we were on this slide, and my question was, do I need to redo those equations? So I just redid those equations. So again, these equations are good for any single vein in which there's one location of entry and one location of exit. So we know what the density is. We have a water jet, so that's not 1,000, well, it's about a little less than that, say 998 kilograms per cubic meter. VR is 80 meters per second. Theta is 170 degrees. And what we now need is the discharge, QR. QR is the relative velocity, which we calculated before, times the approach cross section. So that's 80 meters per second times 0.01 meters squared, 0.08 centimeters per second. And so basically now you have everything to calculate what you were asked to first do. Give me the components parallel and normal to the approach jet. And we're just going to use those two equations. And again, I developed those equations. So here's our moving vein. And here's the x direction equation. Density 998.2 kilogram per cubic meter cubed. Discharge 0.08 cubic meters per second. Velocity, that should be VR. What's that? 80 meters per second, and times 1 minus cosine of 170 degrees. And that gives you 12,680 newtons. And remember, this is approximately minus 0.98. Again, there's a double negative in there. Similarly, Ry is rho QR VR sine theta. And similarly, we can just put in all the information we know, and we find out that the vertical component is really small, and that's because you're turning this thing almost through 180 degrees. If you turn this jet completely through 180 degrees, there would be no Ry. So this is what we just found, Ry, Rx. And I've redrawn what that looks like on the vein. So Rx is really large. It's almost a little more than 10 times Ry. And if we wanted to know the magnitude of the overall vector, the total resultant force, the magnitude of that force would be the Pythagorean theorem, sum of the square root of the sum of the squares. And when we put that in there, we get 12,730 newtons. And then again, we could always figure out the line of action of that force. And in this case, for example, the tangent of that angle would be Ry over Rx. And it's about 5 degrees. Okay, so continuing. This is what we started with. This is the unsteady problem. And the last question you were asked to describe is, what is the rate of work vein? And at the end of last class, I had gone through this, but the rate of work done by the vein is the power. And in this case, the power, if we want to call it the power of the vein, is the x component of the force you just calculated times the vein velocity. So again, a force times a velocity. This force is continually being applied to this vein. And therefore, that is a rate of work that's occurring on this vein. So in this case, we calculated the x component is 12,680 newtons. That was on the last slide. Vein velocity is 40 meters per second, and that gives us 507,200 Newton meter per second squared, which is 507,200 watts, which is 507.2 kilowatts. Okay. So you were asked to get the force components perpendicular and parallel to the approach jet. You were asked to develop or calculate the rate of work being done. If you were just asked to calculate the rate of work being done, you only needed Rx. You didn't need Ry. Again, on an exam, it's all about using your time efficiently. Make sure when you read a problem, you know what is being requested of you. Don't create extra work for you, because let's say this was an exam problem and you were just asked for the rate of work. If you calculated the value of Ry, you know, that's nice to know, but we can't really give you any points for that, can we? Because it's not part of the problem. That's like you writing down what the temperature was and what the weather was outside. It's nice to know, but you're not going to get any credits for that on your homework or your exam. So let's think about what happens before and after this actual moving vein. Before the vein, you have this jet coming at the vein, and all the energy is being held as kinetic energy, V squared over 2G, specifically V0 squared over 2G. So the energy grade line, you know, again, this is a free jet. This is a free jet entering. And so somewhere, remember, the Z direction is perpendicular to the plane of this slide or the plane of this board, is V0 squared over 2G above this surface. That's where the EGL is here. And then the fluid is riding the surface and it's going to leave at V2. So the fluid power before the vein, remember power when we were talking about pumps and turbines. We would take discharge times specific weight times either the power extracted, the energy extracted by the pump, EP, or, sorry, added by the pump, EP, or the energy extracted by the turbine, ET. Well, in this case, we don't have a pump or a turbine. We're just talking about a free jet. What's the power associated with that free jet? Well, it would take all of the energy that you have, and all of the energy is V squared over 2G, multiply it by the relative discharge, QR, notice that, times the specific weight. And that's the power coming onto this vein. And then on the previous slide, we calculated how much power the vein removed. So the vein is going to remove a certain amount of power. And that means you're going to have a certain amount of power leaving. So leaving the jet, again, is V2. V2 is in the real sense. It's not a relative problem anymore. You're sitting there on your sofa and you're watching this thing spinning around. So the fluid comes on at V0 and it leaves at V2. So the power remaining in the free jet after the vein is P2, just like P1 is QR gamma V0 squared over 2G. P2 is QR gamma V2 squared over 2G. All the energy after the vein is held as velocity head because it's a free jet. And so if we know that we had a power entering and we calculated the power extracted by this vein, remember when a vein goes in the same direction as the approach fluid, it's a turbine. So that vein is taking out power. When the vein is moving at the approach jet, it's a pump and the vein is adding power to the fluid. So in this case, if you take the power equation and rearrange it, P2 is equal to this. And so if we bring 2G to the other side, divide by Q over gamma and take the square root, you get this equation. So you're going to see these same equations on the next slide, but we can calculate V2 from the same problem. So again, it's the same slide. Before the vein, all the energy is V0 squared over 2G, 120 meters per second squared, divided by 2 times 9.81 meters per second squared. And that gives us 733.9 meters. So again, if this is the XY plane, 734 meters that way is where the EGL is. The fluid power before the vein is QR gamma V0 squared over 2J, which we know the discharge, again, was V0A0, 0.08 cubic meters per second. Specific weight of water, 9790 or 9800 Newton per meter cubed. And then the V0 squared over 2G, we calculated just above as 733.9 meters. And then I divide that product by 1,000 watts per kilowatts to get an answer in kilowatts. And if you recall, we calculated the vein power in kilowatts as well. So that's the power entering. And then again, we calculated, once we did the momentum analysis, we could calculate how much power the vein was removing. The vein removed 507.2 kilowatts. So basically the power at this location, at the remaining jet, is 68.2 kilowatts. And that power is equal to P2, which is QR gamma V2 squared over 2J. And all we do then is rearrange that equation to get the very last equation on the slide right now. So now that we know everything on the right-hand side, we can calculate the real velocity of the fluid leaving. And so the fluid leaving is leaving at 41.3 meters per second. So again, when you look at this as an observer, it's a very complex situation. Veins going this way at one velocity, the approach jet is coming in another velocity, and the fluid's coming off at yet another velocity in a completely different direction. And you can actually do a vector analysis and figure out the actual direction of V2. V2, I show it like this, but V2 could actually be like that. That's how it's coming off the vein. And you would have to do a vector analysis of the velocities to figure that out. Okay. In the remaining, are there any questions on this? Great. So that was a single vein. There are some very simple modifications we make when we talk about a series of veins. So again, the fan you put in your room or a ceiling fan, they typically have more than one vein. Ceiling fan typically has more than one vein. So in the problem, whenever you see homework problems or exam problems, the first thing you need to assert or assess is it a single vein or a series of veins? It's always going to be clearly in the problem. Although the relative discharge is used for the single vein for forces and power, for a series of veins, all of the flow, Q0, is hitting or impinging on one or more of the veins. And so when we look at the force and the power equations, we need to use Q0 and not QR. So I'm just going to go back to the single vein problem. Yeah. So in the single vein problem, moving vein problem, we're using the relative discharge in the forces. And when we get to the power, that relative discharge, again, is built into this. So when we get to series of veins, we're going to modify these equations. And I put the modification in red. For the single vein, we had QR at this location. For a series of veins, we use Q0. You still have to develop this into a steady state problem. So the relative velocity is always going to be there, but it's the discharge, mass flux is the complete mass flux when you're talking about a series of veins. Similarly, in the Y direction or the other direction, we still use the relative velocity to make this a steady state problem, but we use the full discharge to develop the forces and then ultimately the power. The input power before was QR, gamma V0 squared over 2G. Now it's Q0. The vein power, same as before. And the remaining power, again, Q0. So these are the nuanced differences. When you had a single vein, all of those red Q0s were QR. Other than that, the analysis is exactly the same. You only look at one vein when you're doing the analysis, but the fact that it's in a series means you have to make these adjustments. Clear about that? Questions online? All right, so. So Monday, we are starting a new topic, the boundary layer theory. Monday and all the way to the last day of classes will be on exam 3. Exam 3 is the third exam. It's not a semester cumulative exam. It's just a third exam from the material starting on Monday to the end of the semester. We'll go through boundary layer theory, then we'll go through friction losses in pipes, and then we'll do some open channel flow stuff and we're done. That's the rest of the semester. So today's lecture is on the exam. If I give homeworks tonight, they're going to be on momentum. That's going to be covered on the exam. So there should be no question about what we're covering on the exam. Again, I will set up this time. I can't remember if I published the rooms. We'll post those on Canvas. And then review session will be Thursday p.m.
We have 2 questions. One says, will buoyancy be on the exam? And one says, what chapters exactly are covered in exam 2?
So 2 questions. Will buoyancy be on the exam? I think the buoyancy comes from fluid statics, and I covered fluid statics on the exam 1. If you would like buoyancy, I will put it on exam 1, on exam 2, if you would really like buoyancy. And then the other question was,
What chapters will be covered?
So what chapters will be covered? Do you see these topics? There's something called your syllabus. Go to your syllabus and you'll see what chapters in the book are covered. Syllabus was very thorough, almost lecture by lecture.
We have some more questions.
Sure, I'm listening.
Will forces on curved submerged forces be on the exam?
Did forces on curved surfaces occur before or after acceleration due to fluid masses? That's for whoever asked that question. No answer. So, forces on curved submerged surfaces, like buoyancy, like forces on plane submerged surfaces, is fluid statics. Fluid statics happened before this. If you would like me to put fluid statics on the exam, just let me know, and I will. I think we've covered fluid statics, and we're moving on. Honestly, you have acceleration due to fluid masses and the 3 laws of fluid mechanics. That's a lot to cover. So,
We have no fluid statics, please.
yeah, so as I say, look at the syllabus and you will see these as M members and everything, that all the homework problems, the readings, that is what it covers.
We also have, will the next lab still be due on Friday since it will be due on the same day as the exam?
Do you want the next lab due on the same day as the exam?
No.
I got
No.
a very quick no.
We also have a no.
So
Yeah.
what we did before was make it due on the Monday afterwards, correct? So yeah, that's what we did last time. Is this the 6th lab or the 7th?
It should be
6. So let's make it due Monday. And could one of you post that on
Okay.
Canvas, because I'll forget.
Sure, so
So that lab 6 is posted today, or has it been posted? Or no, it was posted. Yeah, it would be posted today. Yeah,
I'm just gonna look at it.
Yeah, I didn't see the Canvas announcement. Was it posted already?
I think so, yeah.
Okay. So if you can catch Sam before he posts it, send him that note and we'll make it due Monday.
So Monday the 16th.
I can
Yes.
also sort the videos for the second exam for the student to follow easily. But what I did for the first exam,
Okay,
I don't post all the videos to know.
okay. Rusbah said he would organize the videos for you
Second exam.
for the second exam. And they should all be organized by date. But... Any other questions? You're forcing me to let you out early on Friday? That's heresy. Going once. I see somebody's typing.
Yeah, well, we had a question about a crib sheet, but yes, I got a crib sheet.
All right, then that's it. We'll see you Monday. Monday, Tuesday, Thursday, Friday.
We don't have structural on the 18th. This is the day before we all pass.
Oh my gosh. Why?
Because when you teach your course, you can teach whatever you want.
It's open book.
Yeah, the first exam was open book, wasn't it?
Yeah, it was. I keep forgetting.
Yeah.